Hello student, welcome to our lesson today where we are going to look at total internal reflection and its effect. So we start with the total internal reflection. We have that this one occurs or it refers to complete bouncing of light at the boundary between the two media in the optically denser medium. Now, to get a clear picture of total internal reflection, we need to remind ourselves what happens when a ray is coming from optically denser medium to optically less dense medium. We found that when it comes from optically denser medium, that ray is always refracted away from the normal. And when that happens, when we have the total internal reflection, then it implies that all the laws of reflection will be obeyed. So we have this as our diagram. We have the angle of incidence I, and we have the angle of refraction, because now this ray is not refracted but it is reflected. But what happens so that this one can occur? When does this total internal reflection occurs? We have the conditions. One, the ray must be traveling from optically denser medium to optically less dense medium. And number two, the ray or the angle of incidence in the optically denser medium must be greater than the critical angle. And what is critical angle? This is the angle of incidence in the optically denser medium for which the angle of refraction in the optically less dense medium is 90 degrees. So what we are saying is that when this ray is coming from glass to air, it is being refracted away from the normal. So as you increase the angle of incidence, the angle of refraction also increases. And if you find that the angle of incidence is making the ray or the refracted ray to fall on this horizontal line, or in other words, the angle of refraction is 90, then that angle is what we are calling the critical angle. Now, the total internal reflection will occur if the angle of incidence I will be greater than the critical angle. And if it is greater than critical angle, there will be no refraction, but what we shall have is what we are calling the total internal reflection, as shown in this diagram here. We have seen that the ray is coming from the optically denser medium to optically less dense medium. And if that ray, if the refracted ray is falling on this horizontal line, then the angle of refraction will be 90, and this angle is the critical angle. Then from there, let us look at the relationship between the critical angle and the refractive index. Now consider a ray of light striking a glass-air interface as shown in this diagram. We have glass-air interface. Remember, glass is optically denser than air. So the ray is coming from optically denser material to optically less dense material. Therefore, this ray will be refracted away from the normal. This is our normal. So the angle C, which is our critical angle, will be the angle in which the refracted ray is making an angle of 90 with normal. From Snell's law, we know that the refractive index of air with respect to glass will be the sine of C divided by the sine of 90. Therefore, for us to get the refractive index of glass with respect to air, it will be the reciprocal of this. This one is what we derived earlier. And it will be sine 90 over sine C. But we know that the value of sine 90 is 1. Even if now you key in your calculator, and you will find that sine 90 degrees is 1. Therefore, the refractive index of glass with respect to air will be 1 over sine C, where C is the critical angle. Therefore, the refractive index in terms of critical angle is equals to 1 over sine C. And this one we are going to use it, that N is equals to 1 over sine C. Then from there, we can have examples. Example 1. The figure below shows the path of ray of light passing through a rectangular block of perspex placed in air. It is like coming like this, from this part moving like that. You can be able to see that. The arrows always show the direction of the flow of light, ray of light. So you're supposed to calculate the refractive index of perspex. We have derived and seen that the value n is 1 of sine c. So this will be n 1 over sine 43. Our c is 43 because this angle is 90. Therefore, this is our critical angle. So when you key in your calculator, you find that n is 1.467. Again, note that the calculated values must be corrected to 4 significant figures. Then we move to second example. A ray of light travels from a transparent medium into perspex as shown in this figure. We have a ray that is coming from there. Then again, the refracted ray is making an angle of 90 with normal. Which of the two media is optically denser? From here, you can be able to see that the transparent material is optically denser because this ray is being refracted away from the normal. Then number 2, you are supposed to calculate the critical angle C. So from here, we are given the values of theta, or the refractive indices. So n1 sine theta 1 is equals to n2 sine theta 2. So substitute the values. 2.4 sine C is equals to 1.467 sine 90. But we know sine 90 is 1. Therefore, you just need to get the sine inverse of 1.467 divided by 2.4, which will give you 37.66 degrees. And this will be the critical angle of this transparent material. Then from there, we move to the effects of total internal refraction. The first one is the mirage. Now, if you stand on a hot day and you stand on a tarmac road, you always see as if there is a pool of water ahead of you. And as you move, you always find that pool of water moving. That is not a pool of water, but an illusion. So mirage refers to the optical illusion of an inverted pool of water that is caused by total internal reflection of light. Now, during a hot day, air near the ground is warmer and therefore physically less dense than air away from the ground. Therefore, on a hot day, the refractive index increases gradually from the ground upwards. A ray of light traveling in air from sky to ground undergoes continuous refraction, and finally it gets what we call the total internal reflection, as shown in this diagram. So we are saying that during the day, the air that is near the ground is warmer, but the air that is away from the ground is a bit cool. So what will happen is that a ray that is coming from the sky will have to undergo continuous refraction, and at the ground here it will undergo total internal refraction. So due to that, you will find that there is an image. When you are viewing, there is always an image that is formed, and that image appears to be a pool of water. And as you move, you as the observer, your image moves. So that illusion, or that optical illusion of inverted pool of water, is caused by the total internal reflection. Mirages are also witnessed in very cold regions in which the refractive index increases gradually from the ground upwards. The images appear inverted in the sky as shown in this diagram. As you observe here, remember we are saying now it is during the cold regions. So the refractive index is increasing as you move away from the ground. So the image is formed in the sky as shown in this diagram. So these are two cases of effects of total internal reflection. Then from there we have the atmospheric refraction. Now this is a phenomenon in which light rays from the sun are refracted and then reflected internally towards the earth. As a result, you find that the sun is seen even after it has set or before it rises. So in other words, we are saying the sun is not set, or the sun has not risen, and therefore whatever we are seeing is an image. Look at what we have in this diagram. This is where the sun is. You as the observer, you are here. You see the image of the sun because of what we are calling the total internal refraction. We have the atmosphere that is surrounding the earth, and remember, this atmosphere will have different refractive indices, and that is why now we are saying the rays, as they travel from the sun, they will undergo continuous refraction, and at the end they will undergo what we are calling the total internal refraction. And as it refracts, then we have the image being formed. So you as the observer, you see the image of the sun, which is not yet risen. Then from there, we go to total internal reflection prisms. We consider a right-angled isosceles glass or perspex prism to turn a ray of light through 90 degrees. If you have a ray that is coming from this, at this interface, this ray is passing through this part at an angle of 90. So it passes through undeviated. But as it touches this face, you find that the angle of incidence is greater than the angle of, or critical angle. The critical angle of glass is about 42 degrees, but this one is making 45 degrees. So this one is greater, and therefore it undergoes what we call the total internal reflection. As it moves from this boundary again, it has no angle between the normal. The angle between the normal and the incident is 0, and therefore it goes on undeviated. So that way we say that we have turned this ray at an angle of 90. Then from there, we can as well turn a ray of light through an angle of 180 degrees if we place our isosceles triangle here. So this ray is coming from this part. It goes undeviated. On reaching here, it undergoes total internal reflection. And again, in here, it undergoes another total internal reflection. And from here, it moves on undeviated. So we have turned this ray at an angle of 180 degrees. Then from there, we have inversion with deviation. I want you to look at this diagram here, or the object. A ray is coming from the tip of the object, and the other ray is coming from the bottom of the object. They move undeviated at this interface because the angle is 90. So they move undeviated. But on touching this boundary, there is total internal reflection. Again, on this, there is total internal reflection. Again, on this other part, there is also total internal reflection. There is total internal reflection. So you as the viewer, if you place your eye here, whatever you see here is an image that is inverted. So we say that this one, we have inverted, but there is no deviation. But we can have inversion without deviation. This one has a deviation. We can have inversion without deviation when we place our isosceles triangle in this case. So we have an object, a ray is coming from this direction. At this particular point, it is refracted. As you can see, there is bedding. Then at this particular position, the angle of incidence will be greater than the critical angle. So there is total internal reflection. Again here, there is total internal reflection. But in here, there is refraction. And the rays of light, they emerge. So you as the viewer, as you view this diagram, you will see an inverted image. So we have inverted, but there is no deviation. Look at the difference between here. We have deviated here, but these ones, they are almost on the same line. Therefore, this is inversion without deviation. How do we use this? When the prism is used in this inversion without deviation, it has an inverting effect, but with no deviation. And therefore, the object which was upside down, the image will be upright. And therefore, these prisms can be used as erecting prism, the way it is formed here. So if the object was upside down, then you find that the image will be upright. So that is why we are saying it can be used as erecting prism. Then from there we have the assignment. Again, the assignment is testing what we have just learned. So make sure that you attempt and get everything in this assignment. So thank you, and let us meet in our next lesson.